Now we've seen that if we want to work out the electric field at some position near a charged rod of length L, we can do it numerically using Python or Excel or any other programming language and get an answer that's as good as we could possibly want. However, it's just a number. It would be nice to actually get an equation for an answer so we can look at things like how does it go as a function of distance from the rod. And we can do that using the calculus approach, which is what we're going to talk about in this video. If you remember, we have our step equation here saying that the amount of, let's just look at the x component for the moment, the amount of the electric field in the x component is given by this. For the y component, it just has a y on top. That is the amount of electric field x component from one particular little slice over there. So if we want to add them all up, the way we write it is that the total x component is equal to the sum, which is written with the big Greek letter sigma, of all this. So what we're doing is we're summing over y from the bottom to the top, so from minus L over 2 to plus L over 2. Now if we make the delta y smaller, this is going to get more accurate. There are going to be more slices, but if you add them all up, it's going to get more and more accurate. That sounds a bit like, to get perfect accuracy, what we need is to get these delta y's as small as possible, which means we're going to have a very large number of them. If you make them actually 0, an infinite number of them, then it becomes a bit undefined. You're having each delta y is 0, you're having an infinite number of zeros, infinity times 0, not quite sure what that means. So instead of making delta y 0, we will take the limit as delta y tends to 0. So to get this accurate, so at the moment it's only roughly accurate. If we want to make it really accurate, we should take the limit as delta y tends to 0 of all that. Now, when we take the limit, some calculus magic happens. When you have an equation like this with a sum and a delta y, and you know it's going to get more and more accurate the smaller you make the delta y, when you take the limit of delta y tends to 0, it turns from a sum into an integral. So the limit delta y tends to 0 of this, we'll take all the constants outside, so q over L x over 4 pi epsilon naught, those are all constants for the summation. The only thing we're summing over is y, so that's delta y all over x squared plus y squared to the 3 halves. When you take that limit, the sum magically turns into an integral, and the delta y turns into a dy. So this is the same constants at the front, and now it's a definite integral. So it's the integral from y equals minus L over 2 to plus L over 2, 1 over x squared plus y squared to the 3 halves dy. I'm not going to prove that in fact an integral is what you get when you take the limit of a sum, but you can see that in your maths courses. Some say this integral is just a very big S and the sum is a Greek S, so it's just a different way of writing the same thing. That's in general how this works. When you're adding up a large number of things, and it would be more accurate if you can make each slice smaller. You can do it on a computer, make them pretty small, but if you want to make it really accurate, you take the limit, make the slices very, very small, so you have a very large number of them, and the sum turns into a definite integral. Okay, so that's an integral we can do. It's actually a fairly hard integral, but you can look it up in tables of integrals or do it using Wolfram Alpha or something like that. And it turns out that comes out as the Ex component is equal to comes out as y over x squared root x squared plus y squared between L over 2 and minus L over 2. And if you substitute all that in, it comes out as 1 over 4 pi epsilon naught q over x root x squared plus L over 2 squared. And this is now an accurate expression. You can do a similar thing for y. You'd be something for y, ey would have a y instead of an x up there. And that integral comes out as 0. Now here we've got x, but the situation is symmetrical. We could be going any direction out and get the same answer. So we can really replace it with an r. So put r rather than x in there, where r is the distance from the centre, and that would work equally well because it's going to be the same in all directions. So the strength of the electric field at some distance r from a rod of length L is given by 1 over 4 pi epsilon naught Does that look sensible? Well, that's what we're going to find out in the next video.